Well, in the last class we were considering the system with external sinusoidal input and the system itself is a RLC circuit. And we had seen that in such a system the solution will have obviously two components, the particular integral and the complementary function. For the steady state solution, the matter is rather simple, because steady state solution is what we all know from the basic electrical or mechanical engineering, where if this is V m sin omega t, and if you assume the phase to be 0, it is V m 0 degree, and there will be an equivalent impedance of this whole block which say is Z, then the current is V m by Z and then sin omega t plus or minus theta depending on the relative magnitudes of the inductor and the capacitor. So, that is something we know. So, the I p part is V m by Z sin omega t plus phi. The I c part, the complementary function part, would actually be the response of this system when this is absent, okay. And response of this system is a second order system. Its response will be dependent on the dependent on what? If you reduce that into two first order equations, the eigenvalues, it is not eigenvalues, it is eigenvalue, it is a German term. G is always G, so it is an eigenvalue. The eigenvalues, or if you write it in the form of the homogeneous but second order equation, then you have to express it in form of the say I twice zeta omega n in this form, and then depending on these magnitudes you will have either a oscillatory solution or a non oscillatory solution on that. Nevertheless, ultimately if you have a non oscillatory solution, then if you consider in terms of the two eigenvalues, then there will be two eigenvectors and you will be able to write the complementary function, the transient part, as you have C 1 e to the power lambda 1 t times its eigenvector V 1 plus C 2 e to the power lambda 2 t times the eigenvector V 2. This is for non oscillatory solution. Where the eigenvalues are real. If the eigenvalues are complex conjugate, you have I for complex conjugate you have I c is C 1 e to the power, in this case it would be the real part sigma t times it was minus sin omega t cos omega t and C 2 e to the power sigma t cos omega t sin omega t. It is x c in that case. What? Yes, that is the point. Here this omega is what you have applied, and this omega is its natural frequency, because when you are considering the complementary solution, you are considering the homogeneous equation. Homogeneous equation means the forcing part is absent. So, there is no influence of the sinusoid, applied sinusoid. So, remember that these two will be different. So, let us give them names. Let us say this one, the applied one is omega naught or something like that. Fine. The point that I am trying to make is a bit different, because this is what we discussed yesterday. This is x. X means a vector of voltage and the current. So, the current solution I C will be from here, the lower line, it is C 1 e to the power sigma t cos omega t plus C 2 e to the power sigma t sin omega t. That is the current. So, the particular integral was this of the current, and the complementary function is this of the current. So, the total thing, the current I is I as a function of t, I will write it that way, I as a function of t will be the addition of these two. So, first it is e to the power sigma t, I will say C 1 cos omega t plus C 2 sin omega t plus V m by z sin omega naught t plus phi. Okay. That will be the complete solution. The question is, how would you obtain C 1 and C 2? In order to obtain the solution, you obviously have to obtain C 1 and C 2. How would you obtain that? From the initial condition. Good. So, the initial condition of I suppose is 0, because here you have a switch and you turn it on. The moment you turn it on, the current has to be 0, because the inductor was there. Inductor current cannot change instantaneously, fine, the current is 0, but that gives you one equation and two unknowns. How would you solve for C 1 and C 2 then? What? Yes. So, you have to also worry about the initial capacitor voltage, and that together will give you this, but this is the equation that we have obtained in terms of the current. What is the equation in terms of the capacitor voltage? Solution of the capacitor voltage equation. Huh? No, because this is only the complementary function part. But what about the solution in the particular integral? That also we have to worry about. Notice that ultimately your equation was here. Looking at this, the equation was from here. You have this voltage V m sin omega naught t is equal to, first this drop, this is I r plus this L d I dt plus, fine, this was V c. So, V c equation is actually V c was V m sin omega naught t minus I r minus L d I dt. So, in order to obtain the total solution for the V c, all you need to do is to substitute I, this I here, and the derivative of this I here, fine. Algebraically it's a bit messy, but nevertheless not very difficult thing to do, but the moment you do it, you can now put the initial condition for V c, and then you have two equations and two unknowns. Got it? So, how to obtain the actual solution for a system like this? So, do not get worked up if you do not have two equations right away visible here. You have to obtain the V c equation, that can be obtained by two means. First, that can be obtained by two means. One, the complementary function is already available. The particular integral is available here. the particular integral would be available for an equation like this, but that will have to be obtained, that can be obtained separately. There are two possible ways, as I said, either you write equation like this, substitute it here and then obtain the equation for V c, else you start with an equation like this in terms of V c. That means, you write the equation in terms of V c and from there obtain the equation, but it is always to me more advantageous to work this way. That means, you obtain a V c equation in terms of I and then substitute I and d I dt, that gives you equation for V c right away. Okay. So, obtain it, obtain.
How did you choose the second equation as the complementary function for IC? I mean, IC is equal to the second equation of that.
This x c with this as this is actually vector equation. The x c is actually V c I. This is x c. X and its complementary part, x as a vector. Here we are writing its complementary function part. That is why c as a subscript. But what is that vector? It is a vector of V c and I. And that is what we have written down here. Clear? But you do not need that, because once you have written this and substituted that, you get a equation for V c straight away, that includes the particular integral as well as the complementary function part. Fine. So, do this. Okay, I leave it to for you to do maybe later, because it will take a little time, and in the meantime it will be somewhat uncomfortable for me to sit here. So, do it later, but do it, it is a good practice. So, we have seen how to obtain the solution if the external forcing function is either a fixed value or a piecewise constant function, which is a square wave or a sinusoid. What else can you think of as the functional form of the external forcing function? What? Ramp. So, it could be a simple ramp function going on increasing. Yes, it is possible. Anything else? Or maybe a ramp that goes for some time and then goes like this, but nevertheless the solution will be obtained from here, just one, and then that will be repeated. Anything else? Maybe exponential also. I mean, we do not normally come across such functions, but nevertheless we can imagine there could be external forcing function that is a exponential function. So, you can also think of an exponential function. So, here what is the x axis, what is the y axis? F of t as the y axis, t here. So, f external forcing. If it is a electrical circuit, we will say V external forcing voltage, externally applied voltage V of t versus t. Now, in such cases, how would we go ahead to obtain? Notice what was our logic? The logic was that the equation contains of two parts, A x plus B u. A x part only says what is the behavior around the equilibrium point, and the B u part says where is the equilibrium point. So, we first obtain the character on the basis of only A x, and there we found that there can be a few different types of characters, and B u part tells where the equilibrium point is, and if it is some kind of a function like this or a sinusoid or a square wave, we say that it only causes the equilibrium point to move, and therefore, the actual state will, depending on the character of the behavior around the equilibrium point, it will follow. If it is stable, then it is always trying to reach that point while that point is moving. So, that allows us to guess a trial solution. In these cases, what will be the trial solution? If say the applied voltage is is, say in this case A t, in this case it is something A e to the power b t, maybe, right. There will be two things, there will be two unknowns. So, in such cases, how would you guess the trial solution? Now, guessing the trial solution is the particular integral, remember that. We are talking about the steady state solution. In this case, what will be the steady state solution? See, if the equilibrium point moves away as this, the solution will also follow like that. So, it is not difficult to see that the solution will also be a linear function. So, imagine a linear function, say I p, it would be some something dependent on t and some fixed value, that will be general linear function. In this case, how would you guess a trial solution? I p no, what I will do is I will in this I will put the exponent as a e to the power alpha t. Why? Because they have different characters. Alpha is the exponent, that is why I used a Greek letter here, and this is not the exponent. So, it is a normal English letter. So, in this case, what will be the character of this? Notice that ultimately its character has to be such, so that when this is plugged into the equation, it will be able to solve the equation, satisfy the equation, and the equation was a differential equation with derivative part, with double derivative part and stuff like that. So, what should this be? What should this be, so that its derivative is double derivative, and in one side this will satisfy? See what I am trying to drive at. Normally, what will be the equation like? Equation will be that d I d2I dt2 plus d I something say a d I dt plus b I is equal to a e to the power alpha t, that is the external forcing function. Yes. So, yes, that is the point. That is the point, that what should be the nature of I, what can be the nature of I, so that this equation is satisfied. That is what we are trying to guess as a trial solution. The point is that it will never be solved unless the exponents are the same. And so, a trial solution might be b e to the power alpha t. Is that clear? The line of logic. So, the line of logic is where you are trying to guess the solution based on some logic, and the logical structure is clear, that you have the fixed point is moving, and so the actual solution will be following. So, it is logical to guess that the path it will follow, the function it will follow will be of the same nature as the external forcing. Good. So, this will be this trial solution in this case, that will be a trial solution in that case. In this case, what are the unknowns? B1 and B0 and B1. In this case, what is the unknown? B only. So, how do you obtain these? The method of obtaining these is to plug it into the equation and then solve it. That is how you solve. In this case, what will happen? There will be a term that is independent of t in both sides. There will be one term that is dependent on t in both sides. They will individually have to be 0, and that will give you B0 and B1. In this case, how do you obtain B? If you plug it in the equation like this, you will see that B is the only unknown, and you can solve for it. Got it? So, let us do one exercise with this kind of a situation. Suppose you have got a mass resting on a plane, mass of mass m, and suppose it is being acted on by a force which is f e to the power minus alpha t, which means this force itself is exponentially decaying. And suppose at this point there is no spring or anything, but there is a friction, let that be a viscous friction of r. Fine. So, now what will be the dynamical equation or dynamical motion of this mass? That is the question. Can you do it? Do it yourself. I will only help. First point is to write down the equation. So, let us, this is too simple a system. So, we do not need to take all those complicated routes that we took earlier, just balance the forces. D'Alembert's principle. So, it is a mass into acceleration m d v dt plus this force r into v must be equal to f e to the power minus alpha t, right. So, that is the simple equation for this system, or if you write it properly, dv dt is equal to or plus r by m v is equal to f by m e to the power minus alpha t. Okay. Now, what can be a trial solution? Trial solution may be v of t may be b e to the power minus alpha t, exponent has to be the same. Okay. If you put this trial solution into this equation, original equation, what do you have? B e to the power minus alpha t. So, dv dt will be minus alpha b e to the power minus alpha t. So, minus alpha b e to the power minus alpha t, that is this term, plus r by m b e to the power minus alpha t is equal to f by m e to the power minus alpha t. This term cancels off, that immediately gives b, this b that was the unknown, b is f by b comes common, r r minus alpha m. Good. Once we have found b, we can obtain the equation right away. So, the ultimate equation will be, by the way, notice that this will be true only if r is not equal to alpha m. If these are simple parameters of this equation, this could be equal. So, this equation, this whole solution will be valid only when r is not equal to alpha m. Fine. So, once we have obtained this, you have the trial solution is which part? Steady state part. What would be the transient part? Obtain the transient part, drop this, and what will be the transient solution of this? Then for the transient part, you have to take dv dt plus r by m v is equal to 0. What is the characteristic equation? We write this as d dt as p. So, p plus r by m is equal to 0. That is how we wrote it. So, you have the complementary function is
C to the power minus R by n times t.
right. Is V c is some constant e to the power minus, right. So, we now have the task of finding k. How would you find k? Okay, first let us write the total solution. The total solution is V c is k e to the power minus r by m t plus b is this f by r minus alpha m times e to the power minus alpha t, right. And now k has to be obtained from the initial condition, only one unknown. So, if the initial value of V c is known, suppose it starts from rest, V c is 0, in that case k is, wait, if you put t is 0, then this term is 0. So, here remains f by r minus alpha m, here you put t is equal to 0, this term is 1. So, k, this is 0. So, k becomes yes.
Sir, that is not VC.
Oh, oh. Yeah, this is the total V. I was writing the complementary function, and that was the particular part. So, your k is for V at t is equal to 0 is 0, k is equal to what did it come, minus f by r minus alpha m. Now, just put it here, that is the solution. Fine. Okay. Now, I will give you some problems you solve in the next class. Some of them I will try to illustrate. 1. The equation is x 1 dot x 2 dot is equal to 1 minus 1.25 5 and minus 2 x 1 x 2 plus 1 0. Obtain the state 5 seconds after the initial state, say let the initial state be 0 1, not 0 0. Where will the state be? Sketch the vector field and the waveforms. Okay. Noted. So, this problem is straightforward, the way you have already learned. So, I will not go into it, just solve it. 2. The system is like this. here is R M K, and this ground is oscillating with a this ground is oscillating with a sin omega t. Okay. So, obtain the equation for the vibration of this mass. You will see that this arrangement effectively acts as a vibration isolator. That means, if this thing is vibrating, then that vibration will not be will be somewhat less in this as seen as the mass. So, obtain the equation of the vibration of this mass. Okay. How will you do it? How will you do it? In this problem, how will you approach this problem? Tell me first. Bond graph? Fine. So, if you want to draw the bond graph of this, how would you draw? Okay, I'll come back to that. Let me give the problems first. I'll come back to that. So, the third problem is you have got an electrical circuit with an applied voltage which is sinusoidal. Here is the inductor, and here is a resistor, and here is another resistor. But there is a switch here. This is E naught sin omega t. Here is say 1 Henry, here is 10 ohm, and here is 5 ohm. Suppose initially the switch is closed and then it is opened at t is equal to 0. It was closed for a long time and opened at t is equal to 0. What will be the equation for the current? How will you do it? First, when it is closed for a long time, the current at that time was how much? Here is E naught sin omega t divided by by 10. No, is a sinusoid. No, what are you talking about? It's a sinusoid, so you cannot say by 10. This will have its effect, no. So, that depends on the omega. Suppose the omega is 50, then it would be 2 pi f or omega L. So, the omega L will be the impedance of this one and the R, and you have to do it this way. So, this is R which is 10, this is omega L here. So, this Z, and then this E naught by Z sin omega t plus 5. Okay. So, that will be the current flowing when this was closed, and then at a specific time it was opened. Fine. At a specific time it is opened, and then after that what will happen? After that it will be a different R. So, different oscillation, all right, but then there are two parts of this question. What will be the equation, and then where exactly should you open it so that there is no transient? Get the point? So, how do you find it? We already know that you have to open it where the sinusoid is exactly at, if the new circuits, here it was 1 Henry, it will have a particular omega L. Now, the R is 15. For that circuit, whatever is the theta, if this one is opened at that phase angle, then only it will have no transient, else it will have transient. Okay. Okay, now 4. The circuit is now here in this problem, the initially the switch is open, it is not connected to the circuit at all, and then at t is equal to 0 it is taken to position 1, at t is equal to 0 connect to 1. At t is equal to 0.4 second, move to 2. So, initially it is open, at 0 it is connected to 1. So, that you have this circuit, the capacitor not there in the circuit. At 0.4 second it is taken to position 2. In that case, it is only this LC oscillation. Why will it oscillate? Because there was an initial current flowing through this inductor. Now, find out that oscillation. The current waveform. So, what will happen when you have thrown it to 1, you will have the current going like what? It will rise, because initially it was 0, it will rise as, if you allow it to remain for infinite time, how much will it be? It will be 1.5 divided by 0.53. So, current will actually rise like this. It will tend to reach a value 3, but before it reaches at this time. So, you have to find out where it reached, and then at this time what happened? What will happen? What will happen? Okay, fine, oscillation, but what kind of oscillation? Like this? Yes, it will oscillate symmetrically about this 0. So, it will start and go like this, it has to, but then what will be the equation of this? Where will this point be? What will be the value? What will be the amplitude of this oscillation? What will be the frequency of this oscillation? So, there will be these issues that you need to find out. Clear? Five. It is a disastrous problem, because you will have to calculate what happens in an accident. Suppose there is a car moving on a street, and inside one of you is sitting, modeled as a mass, and you have the car cushions and stuff like that, and you have got a seat belt, which are modeled as, say, fine, in both sides you have this, and then there is a wall and this fellow goes and hits the wall. What will be the motion of this mass? The car meets with an accident and it was moving with a velocity v when it hit the wall. Immediately it comes to a stop, right. It was the whole thing was moving with a velocity v and immediately it comes to a stop. This comes to a stop. Assume that there is no recoil, that means it does not, the car itself does not go back, stops. Then what will be the motion of this mass? Huh? Similar to the last problem, all right, and that is what I want you to see, that there are similarity between electrical problems and mechanical problems, but in this case we are giving the initial condition straight away. In this case we gave the initial condition as having in a particular position for quite some time reached a particular value, not steady state, but here we are saying that it has reached the value v, the speed is v and it is moving at a definite velocity v, so that the inside it is at equilibrium position and then it hits. What will happen? Huh? Tell me, what do you see? It will be a damped oscillation, that means this fellow will move like this and then it will oscillate, but then obtain the equation. Engineering is all about obtaining equation. Huh? So, obtain the equation and then solve it and then obtain how exactly will this guy feel. And these are actually done, by the way, these are actually done in order to find out how in accidental situation a particular car will behave. These simulations are actually done. Okay. Now, 6, it is again a circuit problem. There are 2 batteries and suppose here you have a switch and here is another and this is an inductor. It is first order problem. Initially the switch is open, initially the switch is open. So, at t is equal to 0 it is closed. You have to find the waveform for this inductor current I. When it is open, it is this circuit. This is 24 volt, this is 12 volt, this is 60 ohm, this is 30 ohm and this is 0.3 Henry. Well, what will happen? Initially when this is open, you have got a, suppose you have obtained a steady state. In that case, how much will be the current flowing through here? 36 by 90, clear, because it is a DC. And then the moment it is open, it is a different circuit, and where will the steady state be? 12 by 30. So, it is going from one steady state which immediately becomes a transient value, initial value, to another steady state. So, this initial value of 36 by 90 is the initial condition which you have to put in order to obtain the constant. Clear? Fine. Have you noted? 7. Again electrical problem, you have got a battery, you have got an inductor, but there is a switch here and there is another switch here. Again initially both the switches are open. at t is equal to 0, suppose this is S1, this is S2, S1 is closed while S2 remains open. At t is equal to 0.01 second, S1 wait, initially S1 is closed, S2 is opened, and then S1 is opened and S2 is closed. Obtain those who have read a bit of power electronics would immediately realize that this is nothing but the boost converter. So, when we talk about S1 being open, normally this is realized as a by means of a independent switch MOSFET in general, and this is a diode. So, whenever there is a switching on and off, this operates complementarily. So, initially what is the circuit? When S1 is closed, it is only this. What will be the waveform then? Nothing is there. Here you have V is equal to L di dt. So, it will rise linearly with a slope of V by L, simple. So, it will rise linearly with a slope V by L till 0.01 second. So, you have to find out where it reaches, and that becomes the initial condition for the next set of the problem. Now, in the next set of the problem, what you do? In the next set of the problem, this is open and this is closed. So, it is this circuit which is actually L C R circuit. It will give rise to a second order equation, and that second order equation's solution will depend on the values. That means, it could be a non oscillatory, it could be oscillatory and all that. Supposing it is oscillatory solution, so we will give you the numbers, so that it becomes a oscillatory solution, and then you have to solve it with that initial condition that is obtained from the first part, and that will give you the waveform. Clear? So, let us have some values, just check if it will give oscillatory solution, because I want you to do it for oscillatory one. Suppose this is 20 volt, this is 0.1 Henry, this is 100 microfarad, and this is 50 ohm. Dekh lo. I am not very sure if I give these numbers it will be oscillatory, but nevertheless do it. Okay, have you noted? I will take one of these problems, and after this class you just do that in front of me. Okay. Now, you have a cart which is being pulled with a force F. There is a mass m, and here is a friction R. The force is F, or I will write number 10 sine 0.1 t. That is how it is being pulled. M is equal to 50 kg and R is equal to 2 newtons per meters per second. So, what will happen? Here is a sinusoidal forcing, that sinusoidal forcing will make this fellow also sinusoidally move, but not exactly in phase, it will lag in phase. Find out by how much its motion will lag from the phase of this external sinusoidal function. Okay? Fine. Then find out where exactly should you start applying this force, so that there is no transient. It is actually a electrical mechanical equivalent of the electrical problem that you already know, but given a mechanical problem we do not tend to see that it is the same kind of theoretical structure. Okay. Last, you have is a applied voltage, you have got two positions 1 and 2, and this point could either be in 1 or 2, and here there is a capacitor and here there is another inductor and resistor. So, this L1, L2, R, C, this is R1, this is R2, and you have got either this or that, here this E. It was in position 1 for a sufficiently long time, and then it is moved to position 2. So, it goes like this. So, at 1 for a sufficiently long time, during which what happens? What is the circuit? This becomes open, this becomes shorted. So, it is E by R2 that current is established. When it comes here, this is isolated, you have got a homogeneous equation whose solution you have to obtain with that initial condition, that is it. Obtain it with numbers. R1 is equal to 10 ohm, R2 is equal to 5 ohm, L1 is equal to 5 millihenry, L2 is equal to 1 millihenry, C is equal to 100 microfarad. You will have to obtain the waveform for the current and the voltage across the capacitor after 0.1 second. Write it, there is no space to write, so I am not writing. So, after 0.1 second, what will be the voltage across the capacitor? Once you have solved this problem, do it for a sinusoidal source. E is 10 volt. As I said, initially assume it to be DC and solve this problem, but then also do it for 10 sin 50 t. Okay, where E is 10 sin 50 t. Any problem? Fine. Why are we given two inductances? Initially I thought there would be, okay, let me complicate your life. Let me complicate your life. M is equal to millihenry. Okay. But this will actually be trivial. because the same current is flowing through them. It is non-trivial if I place this one here, then it will become non-trivial, but nevertheless do it. The point is that the actual problem is where you assume it to be a sinusoidal source. When you have a sinusoidal source, then this 1, when it is 1, then what is the current flowing through this? It is a RL circuit with this L a bit complicated, but nevertheless that is trivial. So, you have got a RL circuit in which the sinusoidal voltage is applied. So, the current flowing will be V by Z sin omega t plus some phi, fine. While that is going on, is a sinusoidal thing, it is there a long time, means that the transient part, the complementary function part has died down. Now, it is only that sinusoid we are talking about, and now it comes to 2, and obviously what happens after that depends on when it comes to 2. When it comes to 2. Now, if that comes to 2 at the 0 crossing of this, it does not come to 2 at the 0 crossing of the current. Is that right? Because there is a phase, difference. So, the current has some value when the switch is put into the position 2, and then you have to find out the transient with that as the initial condition. Okay, fine. So, now solve these problems, and that will give you reasonably good practice.